We're going to keep building on electrophilic aromatic substitutions and include now groups that are actually on those aromatic systems. What we're going to determine is that there are actually two very different things that we need to talk about having to do when a substituent is actually on an aromatic ring. And really, you have a choice to, in terms of directing groups, to either be activating or deactivating. So we'll discuss that a little bit. And you also have a choice in terms of being either an ortho-para director, which we'll talk about in just a second, or a meta-director. So really, anytime you see a substituent on an aromatic ring, your job is going to be to determine both of these categories before you answer any kind of predict the product kind of question or do any kind of synthesis. And so the activating versus deactivating has to do with, is that group that is put on the ring going to activate it towards that electrophilic aromatic substitution greater than just plain old benzene? Or is it going to somehow deactivate it towards electrophilic aromatic substitution? And again, it's all relative to benzene, right? So benzene, if you want to think about that as kind of the 1 on the barometer, or the 0, or whatever you want to call it. And then everything that is above that is activating, everything that's below that is deactivating. In other words, it's going to be a little bit harder for something that is deactivated to actually have an electrophilic aromatic substitution occur. And then something that is activated obviously is going to be a little bit easier. Another thing which we have to talk a little bit about is, what does it mean to be an ortho-para director versus a meta-director? So the first thing we'll do is that we will draw a benzene ring, and we'll just put some random group out here that I'll call Y. It turns out that these positions on an aromatic ring all have this Greek prefix that goes with their position relative to that substituent, right? So if we look at the substituent and we go 1 carbon over, this is considered what's called an ortho position, which gets a lowercase Greek O. If you are a meta-director, you will direct to this kind of script M position right here, right? You're always 1, 2 carbons away. And then para is this position down here, which is directly across the ring. What you'll notice is there are 2 ortho positions, 2 meta positions, and always 1 para position. It turns out that groups will either direct to an ortho or para position, right? And there's no real easy way to select between those. And by the way, there's no real way to select one side versus the other, at least in a symmetric situation like this. And we'll play around with that just a little bit. But it turns out that you kind of, if you have an ortho-para director, you have very little control over kind of which one of those happens. So it's kind of unsatisfying sometimes in a simple system like this to not be able to really control. There is a little bit of a way to control it, but not something we're going to be talking about too much. And it turns out then that if you're not an ortho-para director, you are actually a meta-director. And notice that there are 2 meta positions. Once again, really tough to control in a symmetric system where the new substituent goes. So these always have to do with some sort of electrophilic aromatic reaction, right? And so I should probably put that on there, right? So I think at this point we've talked about 3 different electrophilic aromatic substitutions. So let's say I wanted to add a bromine. If this Y was meta-directing, I would put it in the meta position. That bromine would substitute in the meta position. Similarly, if that Y, let's say, was activating, right, and an ortho-para director, it would tend to push things in either an ortho or a para direction over that meta direction, right? And so let's take a look at a couple of examples of some of these groups. If all is going according to plan, you should be able to see a resource guide that I've included on your weekly module, and the little picture will appear here. Really is helpful to have that to look at, so I'd print it out or at least have it accessible in some way as you're watching this. One of the things that you should notice pretty quickly is that if you were going to generalize, right, activating groups and also their ortho-para-directing ability, you'll notice that just about every single one of those groups, both of those are true, right? If you're an activator, usually you are some sort of ortho-para-director, right? So let's group those together. And then you'll come over and you'll notice that just about every deactivating group is also a meta-director, right? And so that's also an important thing to kind of group together. So in a lot of ways, that makes our lives a little bit easier because the second that you judge something an activator, you know how it directs in general, right? Same is true of deactivators. And of course, we'll go through in this presentation and you'll be able to recognize when something's activating versus deactivating. The thing that gets really difficult, at least at the very beginning stages, is to recognize which groups are kind of more activating than others. So what I will say is that generally things that have a nitrogen with a lone pair of electrons directly attached to a benzene ring, they tend to be kind of towards the top of the activating ability list. And then in terms of like the deactivators, the very, very lowest, right, the most deactivated, the most deactivating group is kind of an NO2 group, right? And so what we're going to kind of do as we talk about these is all kind of over the course of some homeworks, you'll kind of start to develop, almost a barometer that you've almost kind of memorized, like how activating a certain group is and how deactivating a certain group is. And I'd really start with those, right? Think, some sort of amine, right, is going to be way at the top. Then some sort of nitro group is going to be way towards the bottom. And then we'll kind of fill in everything else. And of course, benzene's right at the middle. So let's go through, and for at least the activating groups here, let's show why these things are ortho-para-directing. Turns out that the majority of what we talk about here is going to be a resonance argument. So let's get dirty. Oh, this being chemistry class, I almost forgot to mention the big exception here. And this is the way that I think is the easiest to memorize this, is that halogens, right, bromine, fluorine, chlorine, and things like that, right, they tend to kind of be deactivators, but also ortho-para-directing, right? And so this is the big exception right here. That doesn't say example, that's an exception, right? The halogens are an exception. They are deactivating, but also ortho-para-directors. Okay, so I think probably the best thing to do is to actually choose some sort of group here. And if you look at your sheet, you'll notice that that is an activator, but also an ortho-para-director. And what we're going to do is I'm going to show you the product that is proper up here, right? And by the way, I could choose ortho or para. My argument would apply equally as well to either one of those cases. So let's just go with ortho. And then down below, hopefully I can kind of scrunch in an example of where if I were to add this particular nitro group meta, what it would look like, and then we'll actually compare the two kind of right on top of each other, and hopefully that'll make the argument pretty clear. First thing we need to know is the note card reaction, right, of how this thing is going to add. Well, take my word for it, that's going to add ortho, and right, we know that this is a nitration, so it's going to put an NO2 group on there, okay? And we're going to go through kind of an abbreviated mechanism. I am not going to show the pot sweetening step, which I definitely showed in a previous video that you should feel comfortable about doing, right? I'm just going to straight up recognize that these two reagents together give me my reactive species that looks like this. Okay? So let's follow the bouncing ball here, and we'll show all the different arrows and resonance forms that we'll end up with to get us to this. And then we'll talk about it in just a sec. Okay, so I've drawn all the resonance forms that we've seen before in the electrophilic aromatic substitution. The only difference is that now I've got this activating group out here with its little lone pair of electrons. And one of the things that you'll notice, because of the position of this pair of electrons, oops, I forgot my other arrow here. Because of the position of that pair of electrons, you'll notice it actually opens up an entirely new resonance form, which looks like an arrow push like that, which hopefully you can see over at the corner here. So now that I've written that, we've got this entire resonance picture. And keep in mind, the idea of resonance is that the more resonance forms that I can draw, the lower the potential energy state of this intermediate is going to be. And because of that, the easier it's going to be for my reaction to happen, right? And we can finish this sucker off just like we would normally do before. Let's say there's some water floating around. And we'll just reach in here and reestablish aromaticity. And we end up with our product. Of course, remember that these, even though like technically this arrow push doesn't show these exact double bonds, keep in mind that that is the same thing as the other. So I guess technically I should probably do it such that I take off the H and it pushes it here, and that pushes there, that pushes there. But either way, that at least explains my product. Okay. Now, let's divide the land into ortho land and then into meta land. Okay, I'm not sure if this is all going to fit. Let's see. Oh yeah, maybe it will. So this is the one that does not happen, right? It's the meta substitution onto this aniline. So let's go through all the same resonance forms that I just showed you. Okay, so hopefully that isn't too small and you can actually see something. So what I would like you to do is I would like you to compare these two resonance images here, right? For the ortho attack and then for the meta attack. Notice that because the positive charge on this particular carbon never gets anywhere near that nitrogen, that I can't actually ever do a fourth resonance form, right? And so this is a pure resonance argument that I'm using right here. This one, when I attack ortho, ends up with 4 resonance forms relative to this one where I only end up with 3. Okay, there's the end of the mechanism. So this is a pure resonance argument. Why this guy adds ortho, right? Now let's change to a meta director, and we'll hopefully I'll just go through and I will erase a couple of things. We'll change that actually to an NO2 group, right? The most deactivating and one of the best meta directors, and we'll kind of see what changes. Okay, so hopefully this isn't a complete mess, but what I've done is I changed every place that we had that amine group formerly, an aniline, and I've changed all of it into a nitro group. And keep in mind that now, for some reason, this is going to be the preferred pathway, right? Because NO2 is a meta director. So why is that? Well, if you compare what we had up on the top here for para-directing in the beginning, you notice that there was a 4th resonance form, right? Well, obviously, if I don't have a lone pair of electrons anywhere directly attached to that benzene ring, that resonance form goes away. So automatically, right then and there, you know, we've definitely kind of hobbled this ortho substitution mechanism relative to the meta. But even more than that, as you go through the different resonance forms, that resonance form is very ugly because you put 2 positive formal charges right next to each other, right? That's bad mamba jamba. If you look at all the different resonance forms for the meta substitution, you'll notice that that positive charge never gets right next to the other formal positive charge. Incidentally, also, this NO2 group is very electron withdrawing, right? So having an NO2 group that's trying to draw electron density out of something that's already has a lot of positive character is pretty bad news. So that's the reason that in the case of nitration and any other electrophilic aromatic substitution, a group like this tends to be a meta director. So what we really have in those two different examples is I used a resonance argument in the first case, the one with aniline or the one with NH2, and now I'm using kind of a combination of an inductive and a resonance argument right here. This is really more of an inductive argument, right? Having to do with positives and negatives and two positives right next to each other and such. What we have in that one crazy exception, which really makes people mad quite often, those halogens, right? You'll notice, well, if I was a halogen, right, I'd have a lone pair of electrons that I could do some sort of resonance stabilization with. And you'd be right, but the problem is that halogens in general are so electronegative that the inductive effect kind of takes over. So even though they're orthoparadirecting, right, that resonance argument right there, they actually tend to deactivate the ring towards any kind of substitution because you've put that halogen right next to a really, really strong positive charge, or I should say a positive formal charge in at least one of those resonance forms. It's very confusing because different groups, you kind of have a different inductive versus resonance effect, so it's not always clear. But this is the first time where these two are kind of coming to loggerheads, having to do with actually solving a problem. All I can do is say, take a look at that list, have that with you in your homework, and we'll kind of hopefully kind of start filling in some of those gaps. And as we practice using some of these arguments, they'll become a lot easier. By the way, I should mention that if I were to put a CH3 out here or any kind of alkyl group, right, they're very slightly electron donating. So it turns out that CH3 groups, even though they don't have a lone pair of electrons to donate and use that resonance argument, they will actually inductively stabilize that positive charge in that resonance form a little bit. And again, that's an inductive effect, not a resonance effect. So I could go through and do the para substitution, and what you would notice is the exact same arguments would apply to both cases. So hopefully this was helpful. Certainly the book does a really great job at explaining this. Ask me in office hours if you need anything.